This is lesson 4, changes in the energy drive. Changes in energy drive the water cycle. Okay, so let's get started. So first it says, can you explain it? Some of Earth's water makes up your body as well as the body of all living things. A tiny drop of water can contain more than 1,000,000,000,000 water molecules. Every water molecule has its own story. Some water molecules at Earth's surface today may have been ingested by a dinosaur 200 million years ago. Think about the last drink of water you took. How do you think that the water may have moved or changed before you drank it? And how do you think that the physical state of water affects its movement? Okay, so the idea that this is telling us here is that this drop of water has literally billions, trillions of actual water H2O molecules that make it up, and those come from everywhere because of the water cycle. So a dinosaur millions of years ago could have taken a drink of water, peed it out into a stream, and those same water molecules evaporate into the sky. They end up being in clouds. They rain down. Maybe it snows somewhere. Maybe it's captured in snow in a mountain for thousands of years. That's kind of what could have happened to the water. And the physical state of water affects its movements. Obviously, if it's frozen, it's not going to move very much, right? You think of glaciers that have been around on continents for hundreds of thousands of years. Those water molecules have been in the same place. That's actually one way that they can tell about climate in the past, right? They go to places with glaciers, which means they're rivers of ice, and they drill down. So like there's like ice, and they get these giant drills and they drill these cylinders out of the ice, and they bring up pieces of cylinders, and you end up with these long cylinders, right? And they have layers in them. They have different layers that you can see. Maybe if a volcano erupted, there'd be a darker layer, and they can look at the composition of the air bubbles in these layers. So in this situation, water is not moving very much because it's there for a super long time. But if it's, like I said, if it's in a river or it evaporates, then it gets moved around a lot more. So exploration 1, analyzing water on Earth. All these explorations are kind of building off this idea of the water cycle, how things get moved around. So look at the photo for evidence of water besides the oceans. Where is water present on Earth? Is it always in liquid form? So no, even in this picture, you can see water in the clouds or the atmosphere. It's also, so that's in a gas type of form. It's also frozen at the poles or in mountains. So it's not just always in liquid form. It could be in gas form, in the air, in the atmosphere. It could also be frozen as a solid. So this is talking about how the importance of water. Some things to note are that only about 2.5% of all of the water on Earth is fresh water. So obviously you look at this, and everything in the atmosphere is fresh water, but that's not accessible to us. And the oceans are all salt water, so that's not super helpful for us because we need fresh water to survive. And 70% of Earth's fresh water is frozen in ice. So of the 2.5% of water on Earth, we can only use about 3/10 of that. So we use far less than a percentage of the water on Earth. So it's important to us. What would not be possible without water? Well, currently today, just thinking about just today, I drank some coffee. That wouldn't be possible with water. Also, I had like breakfast and basically everything with that you need water for. Took a shower, things like that. Okay, states of water. This is discussing how there are 3 states of water that we experience on Earth: liquids down here, gases like in the atmosphere, or solids, frozen water that's in ice. Describe 2 ways that the liquid here could have come here from another location on Earth, or from just how did it get here? Well, all the snow could have evaporated from anywhere on Earth, and then finally kind of snowed down here, and then like the water could have cycled through currents in the ocean from another location. So there's 2 examples. Think back to the dinosaur drinking water. Was this water always in liquid? Not necessarily. It could have evaporated and then rained down, or it could have frozen and then melted over time. So fill in the blank to show whether water gains or loses kinetic energy. So in this first example, we have water gains kinetic energy. As temperature increases, the water molecules in this ice begin to vibrate enough to break free and turn into liquid. So this is going from frozen to liquid, which is more movement, right? If it, in order from the least to the greatest, you would have, you'd have solids, right? You have like solid ice. This does not have a lot of kinetic energy because it's all not moving very much. And then you'd have liquids. This is bad. Liquid. Then you'd have liquids, and then more kinetic energy. The molecules be moving around. Then you'd have, water as a gas. So you can kind of use this key to help you with these. As air temperature decreases, liquid water begins to move slowly until they only vibrate in place. They form solid ice. So this loses. This is losing energy because it's going from a liquid to a solid, so we're losing energy as we go this way. Liquid water begins to vibrate and turns to water vapor, so this gains. I'll just put a G for gains. And as water vapor molecules rise, they enter colder air. They vibrate at a slower rate. Okay, so they're losing. They're losing energy because they're vibrating slower. They're losing kinetic energy. Okay. This is some math. So here you'd have in Celsius, 0 degrees Celsius is 32 degrees Fahrenheit. I have these memorized. And 100 degrees Celsius is 212. I believe. I'm just double checking. Yes, 212 degrees Fahrenheit. You could also use this formula, and the way that you could use this formula, for example, to find this, is you would take this formula and you put 0 degrees Celsius where the C is. So you'd have 9/5 times 0, because it's 0 degrees Celsius, plus 32. And 9/5 times anything times 0 is 0, plus 32, and that's 32, which is why you have this. Okay, exploration 2. The movement of water in Earth's atmosphere. So what evidence of water in the atmosphere can you see in this photo? You can see clouds. These clouds here, that's evidence of water vapor in the atmosphere. There's also water vapor where you can't see it, just spread super far apart, but this is where it has condensed, so you can see it most accurately. It says right here, the atmosphere contains a lot of water vapor, which you cannot see. So you can see it when it condenses, but there's still water molecules in the atmosphere, right? The atmosphere is still made up of molecules of things. Where can water in the atmosphere come from? It can come from all of these. So it would evaporate into the atmosphere. So it could evaporate from oceans. It could evaporate from plants. It could evaporate from puddles. You might think it might not evaporate from ice, but ice does evaporate directly. It's called subduction, and it is. You can actually see it in a freezer. If you open up your freezer and you dig down to the bottom of the ice, if your ice doesn't cycle super well, you'll find like some ice cubes are tiny, and the reason that they're tiny is actually because they're evaporating slowly. Ways water reaches the atmosphere. Oh, did I say? I think up here I just said subduction. It's not subduction. It's called sublimation. That word is right here. Sorry, mixing up my science subwords. So these are different ways that water can get into the atmosphere. Evaporation, I'm sure you're all very familiar with. That's a liquid evaporating to a gas. Transpiration is essentially the same thing as evaporation, but it is a specific word that we use for like water molecules from leaves and from plants evaporating, and there's a specific word for it when it comes from plants, and we call it transpiration. And then there is another word called sublimation that we use. That's what I was talking about here with like the ice in your freezer. Sublimation is when the water molecules essentially on the surface of ice evaporate directly. Through what process might the water have changed and moved before and after the dinosaur drank it? I kind of talked about this when I talked about the dinosaur. Like it could have peed, it could have frozen, it could have gone to the river, things like this. Skip over. Oh, here we go. Microscopic droplets of water in the air grow larger as water vapor continues to condense. What might happen next? Okay, so sorry. What this is describing is you have water vapor, right? You got water vapor in the air. And these droplets are, for whatever reason, they're being attracted more to one another, and they're making larger droplets. So, they're kind of, so the droplets are getting bigger. Okay, as they get bigger, what's going to happen next? Well, eventually it's going to rain. It will. So this is describing, and it's talking about up here, high clouds in the form. Up here it's talking about as you get higher up in the atmosphere, right? So you have clouds, right? And you have clouds at different layers in the atmosphere, right? That's why clouds look different. But as you go higher up in the atmosphere, it's going to be colder. And as it gets colder, the water droplets will tend to condense more, and they will start to gather together. They will form solid ice crystals or liquid droplets, and as they get heavier, eventually the water droplets are too large for them to be just up in the atmosphere. So they get heavy enough that they rain, and that's kind of how rain works. Water droplets condense enough from a vapor into big enough water droplets that they will finally fall. It will precipitate. It'll rain. So precipitation is any form of water that falls from Earth from the clouds. It's a fancy name for, rain, but it also includes things like snow and hail. Snow is just when essentially the water droplets freeze on the way down. Hail is usually if it's really windy and stormy, what happens is the frozen snow droplets will kind of be swirling around up in the upper atmosphere, and the swirling in the upper atmosphere causes them basically like the snowflakes essentially kind of like combine. They get mixed up and combine into larger drops, and then these eventually fall down when they get heavy enough. Deposition occurs when water vapor changes state directly from a gas to a solid. This is the reverse of sublimation. So remember, sublimation was like ice evaporates. Deposition is water vapor, water vapors, gases, going straight to solids. So when water vapor in the atmosphere condenses and forms water droplets, the water molecules, they are releasing energy because they are going from a higher energy state gas to water. So they're losing energy. So they're kind of releasing their own energy. And when liquid water in the atmosphere form ice crystals, the water molecules they're also releasing energy. So they're losing energy. Essentially, they're losing their kinetic energy. So, describe the formation of hail. Oh, I just described this. Describe a time during the formation of hailstones when water releases energy. So, strong winds carry the ice crystals high into the clouds. When the crystals begin falling, they grow larger as more water droplets freeze onto them. Eventually, the hailstones grow too heavy for the wind to carry. That's an example. That's probably the easiest example. They're losing energy. They get too heavy, and so they're losing energy because the wind can't carry them around anymore, so they just kind of fall to earth. And then they'll actually gain kinetic energy as they fall to earth. But the hailstones, the water molecules themselves, have lost energy when they are getting too heavy or when they start to form as well. Exploration 3. Describe the movements of water on Earth's surface. So from photos of Earth's surface, you can see all the locations where water might be. No, you cannot. So there is water. So the short answer is no. There is water underground and frozen beneath the surface. There's that saying, that the tip of the iceberg, right? Normally an iceberg, if this is the ocean and you see like an iceberg, here's an iceberg, generally only about 10%. So the iceberg is probably, this big underneath it. So there's lots of, if you're just looking at photos from the from the surface of Earth, there's water that's underground and caves and all sorts of like soaked into the actual ground. We call that groundwater. But there's also, ice that's underground, things like that. So ocean circulation, I described this earlier when I showed that there was that picture and I asked how could the water get here? And I described ocean currents. So ocean currents, right, just as, depending on where you're at in the ocean, right, it's going to be warmer. The surface of the ocean is much warmer than the bottom of the ocean. The near the equator, it's also warmer than the poles, and that temperature difference, along with changes in the salinity or the saltiness of the water, will create all of these currents. So as ice melts near the poles, it changes like the saltiness of the water, because remember, frozen ice is fresh water. So as it melts near the poles, it's going to kind of decrease the saltiness or the salinity of the water, or where rivers empty out in the oceans, that also changes the salinity. So those things create these currents that move throughout the ocean. You see in an exaggerated, if you've ever seen like Finding Nemo, when they go onto that, I can't remember which current it is. It's probably this one they're describing because it goes by Australia. But they, they get with the turtles, right? And they're on that like current, and they're not really like that, but there's still kind of, you get the idea. And in which ways might ocean currents be like streams on rivers and lands? Well, similar, kind of like they move material around, they balance things out. That's how you can find, if you've ever heard of the garbage patches that are in the middle of the ocean, there's a giant garbage patch in the middle of the ocean, the Pacific. There's a giant garbage patch over here. There's a giant garbage patch here. Why do they settle in certain places? It's just like if you've ever seen a lake or a river and things kind of gather in one place because the water movement, it is the same concept. So it carries stuff around. Water movement on land. What drives the movement of water earth systems? Gravity. Gravity drives all of it. Why are rivers rivers and streams streams? It's because the water is going downhill. Runoff and infiltration. Runoff is water that flows across Earth's surface is called runoff. Sometimes it soaks into the earth, and that's called infiltration. And we call that groundwater. I use that word when I was describing this picture. Groundwater is water that kind of like soaks into the dirt, into the ground. You can see this example here, right? This is showing groundwater soaking into the earth. And we have runoff, which is the rivers and the streams and everything. Which statement correctly describes the movement of water represented by arrows in the picture? Oh, well, we have choose all that apply. Let's see, we have water melting, snow. Yeah, so this snow melting would be these rivers going down, right? That's what would cause the rivers. If you're ever in Tahoe or whatever, where are all those rivers coming from in the middle of summer? It's not raining, they're coming from the snow melting. So there you go. Rainwater seeps into the ground. That's right here. Streams carry water to the mountain peaks. No. Gravity prevents groundwater from reaching Earth's surface. No. So both of these are describing the opposites of what's happening. Right? This is streams carry water to the mountain peaks. The gravity is going downhill, so streams don't go uphill. They can't do that because gravity is pulling the water downhill always. And gravity doesn't prevent groundwater from reaching Earth's surface. Oh, no, sorry. This is true. Gravity prevents groundwater from reaching Earth's surface. So the surface would be like the top of the surface, right? And the groundwater would be the water down here. And so groundwater is going to continue to pull that water down. So that's why you don't just have water popping up all the time. It does actually, we call these seeps or springs, but that's why you only see it in certain places because gravity is preventing that. So there's other things that kind of have to come into play in order for that to happen. In some rivers and lakes, this is talking about dams. Dams form reservoirs, right? You can see here's a dam. There's a giant lake back here. This used to just be a river down like this, but because you put the dam here, it creates a reservoir. That's what a reservoir is. It is that's why we call, like Folsom Lake isn't really a lake, it's a reservoir. It didn't exist until we put Folsom Dam up and it made that big lake. So these reservoirs also disrupt natural systems and cycles. Ecosystems upstream are flooded and destroyed. Downsystem ecosystems that depend on seasonal flooding can suffer from lack of water. What kind of trade-offs need to be considered before constructing a freshwater reservoir can begin? So this is kind of up to you to decide, but there are a lot of trade-offs. In general, dams are seen as positive aspects of dams are that they're usually created to prevent flooding or just to use as electricity. So they are a good source of electricity, but also like if you go to downtown in Sacramento, you'll see how all the houses, right? There's all these houses, all the super old houses. They all have these steps up to the front, and the building is like you'll see that the front door is like here, and the road is like here, but there's like this platform situation happening where it looks like the building is just really high and then there's high steps going up to it. The old buildings look like that because the river used to flood, and so the river would flood, and so they had steps, so the house didn't actually get flooded. Once they built Folsom Dam, it didn't flood anymore, so now people have turned these bottom floors a lot of times into like a whole extra floor of the house. but they prevent flooding and things. But they cause a lot of um, uh, problems downstream. They can disrupt ecosystems. They basically flood anything before it. So there was a town actually where Folsom Dam, where we live, where Folsom Dam is. There used to be a town there, and it's not there anymore because it got flooded. And it also prevents like fish from migrating, and it can kind of ruin entire ecosystems. But again, so the trade-off is that a lot of times they're viewed as ruining ecosystems, but they can produce energy, and they also, they produce a lot of times recreation. Um, they make like for boating and things like that. How might an iceberg move once it breaks off from a glacier? So this is a glacier. This is all frozen ice and gravity. A glacier is basically an ice river, and it moves very slowly. Like you can barely watch it speed. But if you took a time lapse of this over a year, you'd be able to see it move a little bit. But they move real slow because it's solid ice, and that's a glacier. And an iceberg is formed when, so let's say a chunk of this breaks off. So let's say this chunk breaks off, and now that's called an iceberg. So how might it move? The iceberg would just float off into the ocean. It would probably start, and it would melt because it's not attached to the water around it would be warmer, so it would eventually warm and melt completely. Which of the following processes could have caused this cave to fill with water? That would be infiltration. So evaporation is water evaporating into the atmosphere, so it can't be that. Sublimation is solid ice evaporating into the atmosphere, so that's not it. Transpiration, right, that was the word for evaporation with plants, so that's not happening. Infiltration, right, is rainwater soaking into the ground, so that's how you might end up with a cave. And then you can think of ways that water could exit this cave kind of on your own. And finally, model 4, this is modeling the water cycle. So you can see with these pictures how you had ice, and then there's liquid, and then there's less liquid. So kind of what's happening over time would be that this ice is losing energy because it's sitting outside in the sun, or it's warmer out around it. So it loses energy and melts into a liquid. And then if you just leave it there, then that liquid is going to slowly evaporate out. And this is defining the water cycle, which is on a global scale, water constantly moving throughout the Earth system. The process of evaporating and all those things we've been discussing, right? Evaporation, infiltration, sublimation, all these ways that water moves around the Earth is the water cycle. So here's a model of the water cycle. It says, write condensation, runoff, infiltration, and evaporation. So this would be, condensation would be, this would be the green. The green would be condensation, right? It's condensing into clouds. The red would be evaporation, right? It's going from the ocean and the lake up, so that's evaporation. Purple is what did we need? Runoff and infiltration. So this would be runoff, right? The water is running off the land into the ocean. So this is runoff. And then the orangey yellow color is the water seeping into the ground. So that is infiltration. What other processes involve energy in Earth systems are not shown in this model of the water cycle? So this is more talking about what other kind of cycles are there on Earth that aren't shown in the picture. And that would be things like, well, why does the water, for example, why does the water evaporate? Well, because it's not pictured here, but, Mr. Golden Sun is up here. blazing down its radiation onto the water and heating up the water molecules and making it evaporate. So that's an example. Lo and behold, sunlight and gravity, also gravity, right? That's what's pulling it down. Describe what might happen in the water cycle if the amount of solar energy entering the Earth system decreased. So this is if all of a sudden the sun disappeared, right? You wouldn't have a lot of these processes. You wouldn't have sublimation because there's nothing to really warm up the frozen ice, so it sublimates. There's nothing to help. There's nothing to cause evaporation, right? These things are evaporating and sublimating because there's energy from the sun coming. So those processes would stop. And imagine snow on the top of a mountain. What are some ways energy could be transferred as the seasons change? Energy flows from the snow into the snow from the sunlight. That is happening. Cold snow melts into the warmer lake. That could happen. Warmer air absorbs energy from the snow. This cannot happen because warmer air would not absorb energy from the snow, right? You have the snow is cold, right? And the air is hot. So the energy would be going from the air to the snow. The cold snow would be absorbing the hot air. It's the other way around. Energy flows into the snow from the warmer air. Oh, and that's what we just described. So C and D are opposites in this example. And what are some other examples of cycling matter that happen as a result of the water cycle? I kind of mentioned some things up here, but some other examples of cycling matter that happen as the result of the water cycle, I'll go over to this picture here, is an easy example would be, which a lot of people don't think about, but how did this beach get here, right? What is a beach? And beaches are caused by basically the sediments from the land that are being carried down by rivers. And so you have these rivers, and these rivers are carrying water down, but they're not just carrying water. They're carrying all this sediment that they're picking up from the land, and they're taking it to the ocean, and they're depositing it. This is called deposition, which we talk about more later. But that's something that happens. And the deposition or the depositing of all this sediment is where the sand comes from. A lot of people think that the sand comes from the ocean, but actually the ocean is taking all the sand away. And you can actually kind of see that in this picture, how it has where these rivers come out, and there's the water is more brown right here because they're trying to show in this picture, and the ocean current, it says it's moving this way, so the water is moving this way. So they're kind of trying to show how the sediment from these rivers is coming out and being deposited onto the coast. I've talked about this a whole bunch. And finally, we have, remember the water on the bathroom mirror that appears after you shower. Tell a story about how those droplets appear on the mirror and what could happen after the water. Okay, how those droplets appear on the water is, let's say that you have the shower, right, and there's water coming out. And this is hot water. Okay, and then you have your mirror. And your mirror is cold. So as you're showering, a lot of these water molecules are floating around in the air, right? They're like floating around in the air. They have energy. Once they come into contact with the cold mirror, they condense, right? They lose energy, and so they go from a gas to a liquid. And so they start bunching up along the mirror. This is how condensation on like cups and all sorts of things works, and that's what forms that. Describe at least 4 changes. So you can come up with this example on your own because it is about different changes and how the water can move around. But this is this is how condensation kind of works, right? It's the molecules, they're touching something cold and they lose energy and they turn from a gas into a liquid. And finally, draw, and this is a model to go with your story. So that brings us to the end of lesson 4.